Okay, this is like the 8th time that I've started this video, so let's see what happens. Chapter 6.6 transitions from calling energy energy to calling it enthalpy. But for the purposes of what we're doing in AP Chem, the difference is really not anything. Enthalpy is kind of a more all-encompassing word. So we've been talking about energy like literally heat energy. So temperature as heat energy is going from one object to another. Enthalpy is like the big picture. So it's not just heat transfer, but it's like, oh, is the volume changing? Is the pressure changing? Oh, what's going on in here? Blah, blah, blah. But all of the questions that we're doing are assuming that pressure and volume stay the same. So the fact that it's enthalpy actually doesn't really make any difference. And I know that's super confusing, but hey, that's AP chemistry for you. I mean, we can get into it if you want to, but I'm just guessing that you would like to keep it as simple as I would like to keep it. So again, it says delta H, but you can look at it like it says delta E. It's not really that different. One thing that I do want to remind you of is, and we've talked about this, the difference between endothermic and exothermic. So if we're talking about an enthalpy change, we're talking about the overall change in energy of a system during something happening, which can be a reaction, it can be a phase change, it can be dissolving a solution into something, into water or whatever. So if we're talking about something like combustion, okay, combustion reactions are always exothermic, so the delta H, or the enthalpy change of that system, would be negative, because we're saying the system is the reaction, and the surroundings are going to be gaining energy from that, so the system is losing, that's why it's negative. Evaporation. In order for a liquid to evaporate, it has to absorb energy, so the enthalpy change of that system would be positive. In order for a liquid to freeze, it has to lose energy, so the overall enthalpy change will be negative. There are a few questions in the book that just ask you, would the sign be positive or negative for the change in energy for this happening? And you have to think about the direction of heat flow. Okay, so one of the things that I introduced in class today and that I'm continuing with now is the idea that the overall change in energy for a reaction is going to depend on how much of the substance you start with. Okay, so it makes sense if you think about it. Like if you're going to burn 1,000 kilograms of propane, that's going to create a lot of heat. Whereas if you burn 1 gram of propane, it's going to create a very small amount of heat, and it's based on moles. So what we were doing in class today was solving for delta E, just what is the rate of kilojoules per mole during the course of a reaction. But what we're going to do in this video is stoichiometry. So if someone has already figured out delta E and you know that that's kilojoules per mole, then you can use that as in a stoichiometry problem. So for example, in let's see, what page is this? It is on page 268. Okay, so if you have a propane tank that is 13.2 kilograms and you know that the delta E, or in this case the delta H because it's the same, the delta H is, oh my gosh, oh there it is, negative 2,044 kilojoules per mole. Okay, so what this is saying is, here's our reaction. This is propane combusting. Okay, every time 1 mole of propane combusts, it produces, well, theoretically, it produces negative 2,044 kilojoules. So by producing it, we mean it sends it off into the environment, which is why it's a negative. So what we want to look at here, normally with stoich, we'll take, like a gram value of something at the beginning, and we'll turn it into either mass or moles or volume or molarity or whatever of a product. But now we're actually looking at energy, like energy is a product. So we're going to take moles of propane and we're going to convert it into energy because we know that this is the rate that the moles produce energy. So every mole of propane produces 2,044. So we are going to start with 13.2 kilograms, Okay, we know that if we're looking at moles, that's not going to work. So we're going to multiply by 1,000 grams per kilogram, and that's 13,200 grams. Okay, next step for stoichiometry, we have to get moles. So 13,200 grams Every mole of propane weighs 44.09. So that leaves us with 299.4 moles. Okay, so here is the part, this is still propane. There is not really a stoichiometry step now because energy is not a substance, so it doesn't have a coefficient, which basically is the same thing as saying it's always 1-to-1. So we've got 299.4 moles of propane. Every single one of those moles produces 2,044 kilojoules. So our last step is to do 299.4 moles times every mole makes negative 2044 kilojoules. So our last step is to multiply. And the final answer is negative 6.12 times 10 to the 5th. I always run out of room. Kilojoules. Okay, and one more time. Okay, that negative does not mean that it is, getting cold or whatever. It means that this energy is being released by the propane into the environment. So everything outside of the propane would be starting to feel really hot. All right, one more example going in the opposite direction. So this time we are given the simplified balanced equation for burning butane. So that's why there's a 7.5 instead of it being 2, 13, 8, and 10. Whatever. It's ratios, so it doesn't matter. We know the amount of energy produced, and we know the rate of how it's produced, so we can figure out moles, and then go from moles of, and then be able to figure out moles of butane from that. So we're going to start with the value for energy. So we've got 1.5 times 10 to the third kilojoules. Okay, we want to figure out how many moles were used for that. So that is negative 2658. Oh my gosh, I am writing so sloppy. I'm sorry. Oh, one important thing to point out before I go on to the next step is this was written as a positive value for the question, but you have to remember that it's producing 1.5 times 10 to the negative third kilojoules because it's releasing it into the environment. So we're going to have a negative divided by a negative, because if you didn't remember that at first, you would end up getting negative for your mole value, which is obviously not possible. So it should just remind you that you have to switch everything to a positive number. So we have 0.564 moles, and it's already butane because the ratio of energy to butane is always 1-to-1. So now we just need to figure out how many grams that is. The molar mass of butane is 58.14. So we burned a little bit over half a mole. That means that we started with 32.8 grams of butane.